We snap billions of digital photos every single day. We point, we shoot, we share. But what's actually happening inside your phone in that split second? How does it take light from the world and turn it into a file you can just, edit and post? Well, today, we're going to pull back the curtain on the magic of digital imaging.
So, have you ever really stopped to think about it? How does a machine, a piece of metal and glass, translate something like a sunset or a person's face into a bunch of data? That is the big question we're tackling in this explainer.
So here's the game plan. We're going to start our journey with the best camera ever made, the human eye. Then we'll look at how our own vision can be tricked, which is fascinating. After that, we'll dive into how we actually turn light into numbers, what a pixel really is, and finally, how some pretty simple math powers every single photo editing tool you've ever used.
Okay, let's dive right in. Before we can even begin to understand a digital camera, we've got to look at the original blueprint. And that is, without a doubt, the human eye. It is the most sophisticated, most incredible vision model out there, and engineers have basically been trying to copy its design for centuries. And what's wild is just how one-to-one these comparisons are. The lens in your eye focuses light, right? So does a camera lens. Your retina, that screen at the back of your eye, well, that's basically a biological image sensor. And the light-sensitive cells on that retina, the famous rods and cones, they are the natural version of a camera's photodiodes. You can almost think of photodiodes as millions of tiny solar panels, each one designed to turn a little bit of light into a tiny electrical signal.
But your retina isn't just one simple sensor. Oh no, it's got specialized hardware. You've got this massive team of up to 150 million rods that are absolutely incredible at seeing in low light. They're your night vision specialists. And then you have a smaller, more elite squad of about 6 million cones, all packed into the center of your vision, and they are totally dedicated to seeing color. So the eye is this brilliant piece of biological engineering. But here's the twist. Seeing isn't just a physical thing. It's not just about capturing light. Your brain is constantly interpreting all that data. And you know what? Sometimes its interpretation is just plain wrong. And this quote from our source material just nails it. What you think you're seeing isn't always what's actually there. The context, the stuff surrounding an object, can completely change how you perceive it. And this illusion shows it perfectly. Now, I know it's hard to believe, but I promise you, every single one of those inner squares is the exact same shade of gray. But your brain automatically adjusts what you see based on the background. It tells you the square on the light background must be darker and the one on the dark background must be lighter. It's an illusion called simultaneous contrast. Your brain is getting tricked. And it gets even weirder. Your visual system isn't passive. It's an active participant. It will literally fill in gaps in what you see, creating the illusion of a solid white triangle right there where one doesn't even exist. It's connecting the dots for you, trying to make sense of the world. So, because our brains can be so easily fooled, we need a system that can capture light with objective mathematical precision. And that brings us to how a camera does it. This is all about that journey from the continuous analog world of light into a discrete digital file full of numbers. It all kicks off with a process called image acquisition. And really, it's pretty simple. What a camera captures is just a function of two things: a light source in a scene, like the sun, and the way the objects in that scene reflect that light. A shiny red car reflects light very differently than a dark green tree, and the camera's job is just to precisely measure all that reflected light. Now, to turn that scene into a digital file, we have two crucial steps. First step, sampling. Imagine laying a piece of graph paper over the scene. We're just breaking up a continuous image into a grid of discrete coordinates. Then comes quantitation. For every single one of those little squares on our grid, we measure how bright it is, its intensity, and we give it a number. And that's it. Boom. We've just turned light into a big list of numbers. And what do we call those little grid squares? Each with its own coordinate and its own number for brightness? Yep, you guessed it. Pixels. They're the fundamental atoms, the building blocks of every single digital image you have ever laid eyes on. So let's break them down. First, there's spatial resolution. Think of this as the density of our grid, or the pixel density. It's really a measure of the smallest detail we can possibly capture. You know when you zoom way in on a photo and it gets all blocky? You're literally seeing the individual pixels. But when you pack more and more pixels into that same area, often measured in dots per inch or DPI, you get high spatial resolution. And that's what gives you those super sharp, crisp, detailed images.
Okay, so that was about how many pixels we have. The second key property is intensity resolution. This isn't about the number of pixels, but about the information each individual pixel can hold. It's about how many different values for brightness or color we can assign to it. This is what determines the richness of an image, the number of shades of gray, or the millions of colors it can show off. And this is all controlled by something called bit depth, the number of computer bits used for each pixel. And check out this table. Adding more bits has an absolutely explosive effect. A 1-bit image, it can only be pure black or pure white. That's it. But an 8-bit image, which is the standard for most photos you see, gives you 256 distinct levels of intensity. But then jump to a 16-bit image, whoa, now you have over 65,000 levels. That is a massive leap in tonal information.
So why does any of this matter? I mean, who cares, right? Well, just look at this comparison. On the left, you've got a nice, smooth gradient with 256 levels of gray. On the right, with only 32 levels, you can see these ugly, distinct bands where the shades just abruptly change. That effect is called banding, and it's what happens when you just don't have enough intensity resolution. All right, so let's tie all of this together into something really powerful. We've established that an image is just a grid of pixels, and each pixel is really just a number representing its brightness. Well, if that's true, then it means we can manipulate images just by doing math on those numbers, right? And that is exactly what happens. All of those complex operations, all those fancy filters and programs like Photoshop, they're all built on a foundation of super simple pixel arithmetic. Want to make an image brighter? You just add a value to every pixel. Darker? You subtract. And multiplication and division? Well, those can be used for some really cool advanced techniques, like masking. Let's look at a practical example of this, using multiplication. A lot of the time, you don't want to apply an effect to the whole image, just one specific part. To do that, first we have to define what's called a region of interest, or an ROI. It's basically you telling the computer, hey, just perform your math on the pixels in this specific area and ignore the rest. And the way we isolate that ROI is wonderfully simple. We use a mask. A mask is just another image of the same size, where the area we want to keep is pure white and the area we want to get rid of is pure black. In the language of pixels, that white has a value of 1 and the black has a value of 0. And now for the magic trick. We literally just multiply the original image by the mask, pixel by pixel. So think about it. Any pixel from our original image that gets multiplied by a black pixel, a 0, becomes 0. It's gone. It disappears. And any pixel multiplied by a white pixel, a 1, remains exactly the same. And just like that, using simple grade school multiplication, we have perfectly isolated our object. And that brings us to our final thought. We've gone from the biology of the human eye all the way to simple arithmetic. Every stunning filter, every complex edit, all of that photo magic is, at its core, just math being done on a grid of numbers. So if that's all a photograph really is, how does that change the way you look at the next picture you take?